Welcome to the PrepNet, presented every Sunday at 6 p.m. Eastern Time on Talk2Me's Channel 14. Come join us to discuss everything about prepping and hear what others have done. All about communications. Communications Modes, Part 1. We are going to talk about the different communication modes that can be used over the radio airwaves. If you have spent any time listening to the bands, you have probably heard signals that sound very different from one another. Some sound like normal voice conversations, some sound like buzzing or tones, and others may sound like rapid beeps. Those different sounds are created by different communication modes. Each mode was designed to solve a particular problem, such as improving range, reducing bandwidth, working in noisy conditions, or allowing computers to communicate over the air. Understanding these modes helps an operator choose the right tool for the situation. We will explore several of the most common radio communication modes. For each one, we will briefly discuss what is the mode, how it works, its strengths, its limitations, and where it is commonly used. Before we start listing them, it helps to understand what the word mode means in radio. A radio mode is simply the method used to place information onto a radio signal so it can travel through the air and then be recovered by another radio. In other words, it is the technique used to carry your voice, text, or data over a radio wave. Different modes change different parts of the radio signal. Some modes change the amplitude of the signal, others change the frequency, and others convert the information into digital tones that computers can decode. Because of these differences, each mode has advantages and disadvantages depending on conditions and equipment. We will begin with the voice communication modes. These are the modes where operators speak directly to each other using microphones and speakers. The voice modes we will cover are amplitude modulation, frequency modulation, single sideband, and digital voice. After that, we will move into several of the digital text communication modes. These modes usually involve a computer connected to the radio. The computer converts text into audio tones that are transmitted by the radio and decoded by another computer at the receiving station. Some of these modes are designed for weak signals, while others are designed to pass accurate text, even in difficult conditions. Digital modes we will discuss include radio teletype, PSK31, Olivia, JS8 call, and finally we will talk about continuous wave. By the end of this discussion, you should have a basic understanding of how these different modes work, why operators use them, and what situations each one is best suited for. Now let's begin with our first voice mode. Amplitude modulation, usually called AM, was one of the earliest methods used to transmit voice over radio. With AM, the strength of the radio signal, called the amplitude, is increased and decreased in step with the sound of your voice. When you speak into the microphone, your voice creates an audio signal. The radio uses that audio signal to vary the power level of the transmitted radio wave. Those variations carry the information through the air. At the receiving radio, the receiver detects those changes in signal strength and converts them back into audio that can be heard through the speaker. The strengths of AM. AM equipment is relatively simple and easy to understand. It provides natural-sounding audio when the signal is strong. Because it was widely used historically, AM is still used in several services, including aviation communications, standard AM broadcast radio, and CB radio. On standard CB channels, AM is the primary voice mode used for everyday communication between operators such as truck drivers, travelers, and hobbyists. CB and amateur radio both use AM, but they are usually heard in different ways. CB radio is limited to lower power levels and a small group of channels around 27 MHz, and conversations are often short and informal. In amateur radio, AM is usually heard on specific portions of the HF bands where operators enjoy experimenting with equipment or operating vintage radios. Amateur stations may also run higher power and larger antennas, which can allow AM signals to travel much farther. Limitations of AM. AM is not very efficient. A large portion of the transmitter power does not actually carry useful information. AM also requires more bandwidth than some other voice modes. Another limitation is that AM is more susceptible to electrical noise and interference. However, an AM receiver can act as a rough lightning detector, as you will hear sharp crashing sounds when lightning is nearby. In aviation, pilots may notice these static crashes on AM airband receivers, which can provide a general indication of nearby thunderstorm activity. This is not a substitute for weather radar, but it can serve as an additional awareness tool. Because of these limitations, other voice modes such as FM and single sideband were developed to improve efficiency and performance. So why use AM in aviation? A common question is why aviation communications still use AM instead of FM. The main reason is safety. With AM, if two aircraft transmit at the same time, the signals will mix together, and both transmissions may be heard at once. While the audio may be messy, pilots and controllers can often still recognize that two stations transmitted simultaneously. With FM, the receiver usually captures only the strongest signal and completely suppresses the weaker one. This is called the capture effect. If two aircraft transmitted at the same time using FM, one transmission could completely block the other without anyone realizing it happened. Because aviation communication is safety critical, pilots and air traffic controllers need to know if overlapping transmissions occur. AM allows that to happen, which is why it continues to be used in aviation radio systems. Bandwidth comparison example. To understand why newer voice modes were developed, it helps to compare how much radio spectrum, or space, different modes typically use. A typical AM voice signal may occupy around 6 to 10 kHz, or 6,000 to 10,000 Hz of bandwidth. An FM signal used on VHF amateur repeaters and GMRS UHF repeaters is usually around 12 to 16 kHz wide. Single sideband, however, usually only occupies about 2 to 3 kHz. That means several single sideband signals can fit into the same amount of spectrum that a single wide FM signal might use. Because single sideband also uses transmitter power more efficiently than AM, it became the preferred voice mode for long-distance HF communication. Another way to look at this is by comparing how many signals can fit into the same amount of spectrum. In the space required for one typical 15 kHz FM signal, you could fit roughly 2 AM signals. In that same amount of spectrum, you could often fit 5 or even 6 single sideband signals. This efficiency is one of the main reasons single sideband became the dominant voice mode on the HF amateur bands. Next, we will look at frequency modulation, or FM. Frequency modulation, usually called FM, is another method used to transmit voice over radio. Instead of changing the strength of the signal like AM does, FM changes the frequency of the radio signal in step with the sound of your voice. When you speak into the microphone, your voice creates an audio signal. In an FM transmitter, that audio signal causes the transmitted frequency to shift slightly higher and lower around a center frequency. Those small frequency changes carry the information through the air. At the receiving radio, the receiver detects those frequency variations and converts them back into audio that can be heard through the speaker. Strengths of FM. One of the biggest advantages of FM is its audio clarity. FM receivers are very good at rejecting electrical noise and static. As long as the signal is strong enough, the received audio can sound very clean and easy to understand. Another characteristic of FM is the capture effect. When two signals are present on the same frequency, the receiver will usually lock onto the stronger signal and suppress the weaker one. This behavior helps reduce interference in many local communication systems. Because of these advantages, FM is widely used for local communication services. FM is commonly used on amateur VHF and UHF repeaters, handheld radios, mobile radios, and many public safety and commercial radio systems. Services such as GMRS, many business radio systems, and older public safety radio systems also commonly use FM. Limitations of FM. One limitation of FM is that it requires more bandwidth than many other communication modes. As we discussed earlier, a typical FM voice signal may occupy around 12 to 16 kHz of spectrum. Because of this wider bandwidth, FM is not usually used on the crowded HF bands where spectrum space is more limited. Another limitation is that FM generally works best for relatively short-range communications. FM signals tend to operate in a line-of-sight manner, especially on VHF and UHF frequencies. Terrain, buildings, and the curvature of the Earth can limit how far those signals travel. To extend coverage, many FM systems use repeaters. A repeater receives a signal on one frequency and retransmits it on another frequency, allowing stations that cannot hear each other directly to communicate. Because of its clear audio and simple operation, FM is often the first mode new radio operators use when they begin operating on VHF or UHF radios. Next week, we'll continue with the rest of the voice modes. If you have any questions about what we have discussed here tonight, please send your question to prepnetch14@gmail.com and enter question in the subject line.